Hello everyone. Today I will be presenting a brief overview of how generative AI, or known as Gen AI, is transforming organic chemistry, particularly in structure prediction and spectral data interpretation. So, what is generative AI? Generative AI refers to a machine learning model that can create new data based on patterns in existing data. In chemistry, this means that generating new molecular structure, predicting reaction pathway, and interpreting spectral data. Of this presentation video and the report assignment is to critically analyze how Gen AI is shaping the way scientists work in organic chemistry, especially in research and discovery in medicine, environmental science, and industrial chemistry. So, this analysis is based on two academic articles. First is by Pierti and Brunel 2018, which provide an early look into Gen AI's role in reaction prediction. Second academic article is by Muloni et al. 2023, which explore the latest application of deep learning and natural language processing in drug discovery and structure prediction. Let's first look at the first academic article by Pierti and Brunel 2018. In this paper, Pierti and Brunel explain how tools like Chematica use expert-defined rules and scoring system to suggest optimal synthesis routes. They also highlight the use of sequence-to-sequence neural network for predicting chemical reaction, which is essential in translating chemical inputs and outputs useful for retrosynthesis planning. Retrosynthesis planning refers to a backward reaction pathway. For example, Segler's model trained on over 12 million reactions that could suggest multi-step reaction pathways, while IBM's model achieved 80% top 1 accuracy in predicting forward reaction based on just under 100,000 examples. While there is no drug that has been fully synthesized by AI at that time, the author emphasized AI's value as a tool to help chemists boost their productivity and not replace them in research. Second article, Mulani et al. Provide a more recent and comprehensive look on how AI is being used in the natural product drug discovery. They focus on the power of deep learning and natural language processing AI to predict how natural compounds are built, what they look like, and how they behave biologically. One key model that they highlight is DeepBGC, which detects gene clusters responsible for making bioactive molecules and predict their function based on protein signatures. Another model, DeepRIPP, combines neural networks with natural language processing to identify early-stage natural products straight from genetic data. The paper also introduced tools for spectral data interpretation. For example, K-System and SMART 2.0, a convolutional neural network, help predict molecular structure directly from AMR or MS spectra without using prior chemical template. Using these tools, researchers have successfully identified complex molecules, for example, symplocolite, by letting Gen AI search through biological samples and match spectra with candidate structures. More exciting is the combination of different data types. Muloni and his colleague show how genetic, metabolomic, and structural data can be combined in AI model to link chemical structure with biological targets, which is an important step into true AI-powered drug design. They also explore graph neural networks and encoder-decoder models to generate visual and functional prediction of molecular behavior. Last but not least, while these advancements are promising, the authors also warn that the model accuracy depends on high-quality, well-annotated data. Poor training data and biased dataset can lead to misleading results. Rigorous training and validation is important to build a trustworthy AI system for chemistry.
AI as an organic chemist assistant. Both articles emphasize how generative AI is becoming a powerful assistant for organic chemists. It's helping in compound synthesis, reconstructing natural pathway, and predicting bioactivity. For example, Mullow and colleagues show that deep learning model can link genetic and chemical information. This allows scientists to connect gene cluster with the chemical compounds they produce, especially helpful when studying microbes involved in antibiotic development. Meanwhile, Pirate and Brunel discuss how early Gen AI tools were already assisting in retrosynthesis. This model suggests reaction pathway just like an expert would, freeing up researchers to focus on evaluating optimizing results. Okay then, one key benefit of Gen AI is speed. What used to take weeks in the lab can now be done in just a few hours, perfect for last-phase drug discovery. Another advantage is the ability to access previously hidden or unexplored chemical spaces. Natural products are often complex, but Gen AI module trained on genomic and metabolic data can reveal new biosynthetic pathway. For instance, Maloney team managed to predict new ribs like pristine A3 and deep flavor that traditional approach would have missed. And finally, Gen AI costs and waste and reduce costs and waste. By narrowing down promising candidate early, researcher can focus resources on the compound most likely to succeed. That's all from me. Thank you.
Hi, my name is Tajia and I'll present to you about challenges and limitations of generative AI in organic chemistry. Despite all the benefits of generative AI in organic chemistry actually faces critical challenges. First is data dependence and bias. As Maloney 2023 warned, the training of Gen AI models will rely on access to large, diverse, and high quality of data sets. Many available chemical databases are biased towards synthetic molecules, leaving natural product space underrepresented. This can lead to models that generalize poorly when confronted with novel structural classes or rare biosynthetic logic. Another issue is the lack of interpretability, especially in deep learning-based generative systems. The black box nature of predictions means chemists may not understand why a specific pathway or structure was suggested. This impairs trust and hampers the integration of Gen AI in regulatory and experimental validation. Peretti and Brunel 2018 echo this concern, stating that while generative AI can suggest answers, it doesn't always explain how it came to the conclusion. There are also computational and resource-related limitations. High-performing generative models demand considerable computational power and storage, resources that may be inaccessible to researchers in developing countries or smaller institutions. This poses a risk of creating a digital inaccess to cutting-edge discovery tools. For ethical consideration in Gen AI. Generative AI also introduces nuanced ethical concerns. One of these is algorithm bias, particularly if training datasets reflect historical neglect of disease common in low-income regions. This could inadvertently perpetuate inequities in global health research. For example, if generative AI is trained predominantly on antibiotics relevant to Western pathogens, it may not suggest compounds effective against tropical disease. And ownership are additional concerns, especially when models use proprietary genomic data or patient-derived datasets for training. Maloney 2023 emphasized the importance of transparent data governance, particularly when community-generated databases are used. Finally, the responsibility and accountability of AI-generated recommendations remain a gray area. If an AI-generated structure results in adverse outcomes in a therapeutic context, determining responsibility, whether it lies with the developer, chemist, or institution, becomes ethically and legally complex. Next, we will look at application of generative AI in real life. First is drug development and natural product engineering. Generative AI has become a key driver in the discovery and design of novel bioactive molecules, especially within pharmaceutical pipelines. According to Maloney 2023, Gen AI models are now deployed in pharmaceutical research to interpret biosynthetic gene clusters, BCGs from microbial genomes, and predict the structure of corresponding natural products without requiring their physical isolation. This capability is especially valuable for rare or unculturable organisms, enabling drug developers to access novel chemical scaffolds that were previously hidden in genomic data. Moreover, structure generation using generative AI has led to the identification of lead compounds with promising therapeutic profiles in antimicrobial, anti-cancer, and neuroprotective domains. Pharmaceutical companies have started integrating these models into early-stage screening to prioritize molecules with predicted high potency and desirable pharmacokinetics, effectively shortening the discovery to development timeline.
For me, 4.2, precision fermentation and industrial biosynthesis. In industry, generative AI helps make microbes like bacteria work better to produce useful things like enzymes, vitamins, and special chemicals. According to Parity and Brunel 2018, AI can plan the best way to make complex molecules, helping scientists control how microbes produce them. For example, Gen AI can predict each step needed to get a final product. This allows scientists to know which genes to change in bacteria like E. coli or streptomyces so they can produce more efficiently. For 4.3, clinical application in structural metabolomics, Gen AI is now used in clinical metabolomics which studies chemical in patient samples. When lab tools like mass spectrometry (MS) or NMR detect unknown chemicals, Gen AI can predict how those chemicals might be, analyzing the signal patterns and comparing them to known data. This prediction help find biomarkers, sign a disease like a cancer, metabolic disorder or infection. In personalized medicine, Gen AI helps doctors choose better treatments by identifying chemical pattern linked to disease or drug response. This makes treatment more accurate and effective. 4.4 Natural toxin identification and environmental monitoring. In environmental chemistry, Gen AI helps identify unknown natural toxins in places like soil, water, or the ocean. According to Mulowny et 2023, AI tools have helped find new toxin produce. AI tools have helped find new toxin producing genes in bacteria like cyanobacteria and actinomycetes. Gen AI can predict toxin structure even before they are discovered, which help in early detection and risk control for health and farming. Gen AI also used to predict how pollutants break down. By modeling the breakdown products, scientists can plan better ways to clean and monitor pollution.
Assalamualaikum everyone, I'm Azmin bin Azman. We'll be presenting a real-life application of AI, especially in a smart laboratory platforms. In advance, laboratory Gen AI has been built into the automated system that can perform chemical synthesis of known as a robot chemist. Thus, a system combines generative AI models with a real-life experiment, allowing for a structure suggestion to be immediately followed by automated creation and analysis. This creates a continuously feedback loop where AI-generated structures are verified on the spot, making ongoing discovery and improvement. Such systems are now in use in drug and material research lab, enabling them to test 100 of a different structure variation in just a few days. This hugely boosts productivity while simultaneously reducing human errors and lowering research costs. To conclude, artificial intelligence is changing how a chemistry works in the organic chemistry. It helps them predict chemical structure faster, more accurately, and with more creative ideas. AI has made it possible to do things that were too hard or slow before, but it also brings challenges like unfair data, hard to understand results, and limited access to powerful computers. That's why it's important to use AI in the responsible and fair way. As we explore what AI can do, we must also think about what it should do. The goal is not to replace a scientist, but to work together, combining human thinking with AI tools solving big problems. With a smart and careful use, AI can help scientists grow and support global health and fairness. Thank you.